Alright, this is the start of the new series of what I will call statistical forecasting. So in the previous series, I covered multivariate regression. A lot of that which includes time series variables, and so I'm going to be continuing that time series aspect, starting with single variable forecasting, single variable time series analysis, and eventually I'll move on to multivariate forecasting and regression. But for now, I'm going to focus on kind of the single variable time series forecasting aspect where the series is kind of more focused on forecasting rather than the analysis. Obviously, the analysis is crucial to the forecasting part, so there'll still be a lot of analysis, but the whole point to this new series I'm starting is to kind of use that regression analysis to predict the future. Alright, so for the intro to this video, I'm going to start by starting with these properties. So first order and second order properties. When we inspect data, inspect a time series, single time series plot, we will start out with kind of just like generalizing how the data looks like. So look at the trend, seasonality, and cycles. We're gonna go over what that is, but just very basic and general viewpoints on how the data is moving, if it's moving up or down, how much it's fluctuating. But then once we do that, we're going to use more mathematical properties to see how objectively the data moves, and whether how much it is fluctuating, whether it's correlation. And so we'll use those type of functions to see if it's really moving or not. So similar to heteroscedasticity, it's useful to get a general visual to see, sometimes it's completely obvious that there is heteroscedasticity, sometimes it's hard to tell. So, and that's what we're going to be doing for the time series single variable movement as well, where we learned that we don't want stationarity and correlation within the plot when we want to analyze how the data is moving. So that's what we're going to do. Those are the second order properties we're going to utilize to make sure there's no autocorrelation and stuff like that. So like I said, a forecast is basically a statement about a future, and we have different types of forecasts. So a point forecast, where we just forecast a single number. What's going to be the stock price of Amazon in a couple of days or 3 days, and then if we say a single number, that will be a point forecast. If we give a range of values, so 200 to 300, that's what we call it interval forecast. And a density forecast is the most specific. So that's the probability distribution, similar to like a histogram. So what will be the percentage of Amazon being from 200 to 300, and then we can kind of give a percentage of that interval happening. The forecast horizon is what is a number that represents the number of periods between today and the end of the forecast. So if it's today is Monday, and so if we want to forecast the price of Amazon from Tuesday to Friday, then that will be, Tuesday, Wednesday, Thursday, Friday. So 4 days, so 4 units of the forecast horizon. And then this is just and then this is kind of dissecting more into the horizon. So the first one is saying The first one is only concerned with finding the value that's only 8 steps ahead. So if we want to find the stock price of Friday only, that's what we would use the 8 step ahead forecast for. So only Friday, the stock price of Friday, whereas the extrapolation method, we are concerned with finding the stock price of Tuesday, Wednesday, Thursday, Friday. Pretty simple. All right, like I said, the starting with the first order properties, we have the trend, cycle, and seasonality, which are the basic kind of descriptions of how we can kind of analyze a single variable time series data plot. And so what I did was draw 4 plots to represent the 3 kind of different combinations of these 3 properties. And so if we're looking at the first plot, we see a clear upwards increase over time, whatever this y variable might represent, we don't know. Doesn't really matter in this case, but we see that there's a clear upwards y value increase over time, and that's what we'll call the trend. So there's a clear upwards trend, and trend is only up or down. So if it's horizontal like this, then we wouldn't say there's a trend, or clear trend at least. So clear upwards trend. We'll go with the seasonality second. So seasonality is kind of these smaller patterns that occur within the trend. So looking at the first plot, there is a pretty clear seasonality of, if this is like 1 year, then there's a, upward spike every year. Probably, if we can infer, then probably during the middle of the year. And so it'll move significantly up and down, and that's what we'll call the seasonality. And then the cycle is a bit more confusing. You can almost think it as the seasonality, except it's a lot over a longer period. So the cycle usually happens over many periods of years. So there's actually no cycle in this case, but when I go to the later graphs here, that's when I'll demonstrate that there is a cycle. Looking at the second plot here, for example, no clear trend, as I guess it's moving it slightly upwards, but visually we wouldn't really see it as a trend. Seasonality, very small spikes of seasonality. So overall, we would say there is seasonality, kind of these very quick movements of up and down. And then the cycle is, again, it happens over several years. So we can kind of see this. Think of like, if you remember cosine or sine graphs, where we have these very fluid, smooth fluctuations or smooth curves. So kind of like these very big curves that are we can distinguish from the seasonality, and that's what we'll call a cycle. And this happens over several years. So that's the time aspect is how we can distinguish from the cycle from the seasonality. Plot 3, clear downwards trend. Clear seasonality, very pointy spikes, but we'll still say there's a seasonality, but no cycle. And then plot 4, clear upwards trend, clear seasonality, and actually, okay, so my bad. For seasonality, we generally want the these fluctuations to be consistent over time. So the third plot, for example, the first 2 we have generally pretty consistent up and down movements, these small spikes. But for plot 3, we see that the seasonality fluctuation isn't very consistent. In the middle it's very big. At the start it's a little smaller. So we actually wouldn't. It is subjective, but just from the general viewpoint, I wouldn't say there's a clear seasonality here. Opposed to these first two graphs where these fluctuations are fairly consistent. The fourth one, I would say there's seasonality. Again, these up and down movements are fairly consistent. Pretty clear upwards trend, and I would also say there is a cycle here of kind of this wave motion. And so the formal definition of a trend is a slow long-run evolution in the variables. So the least specific, think of like the overall movement, the broad long run. We have types of trend. So deterministic trend is a clear and predictable trend. I listed numbers here for the graph, so 1, 3, 4. And then 2 is the stochastic trend, where we have a more unclear and predictable unpredictable trend. And in like engineering and physics, often we observe these type of plots, but in data analysis and economics and whatnot, when we're analyzing financial data, these are realistically the type of data that we're going to analyze, because analyzing these type of graphs are pretty inaccurate when it comes to forecasting. We usually want it to be stationary and non-autocorrelated in order to forecast, so that we can get a more accurate forecast and remove bias from all these spikes and trends. So types of seasonality, the additive and multiplicative trend. And so again, I mentioned kind of the consistency in like the absolute value of these variations over these spikes moving up and down. And we do generally want it to be consistent, but obviously they're not always going to be the same. And so the additive is what we'll use. Additive property is what we're going to use when these fluctuations do not vary much with time. And the multiplicative is what we'll use to is when we observe that there's a lot of variations in time. So kind of like this, there, right? 2, 3. So I guess, okay, so plot 2, I guess, you know, these are pretty consistent, but there's a big spike upwards here, here, here. So I guess changing my opinion from previously, you know, we can conclude that the seasonality here isn't very consistent. And so when we want to, you know, remove the seasonality aspect and only dissect the trend and maybe the remainder, then we'll subtract the y, the overall model, from the seasonality. But then when there's a lot of fluctuation, we'll kind of scale it down by dividing the seasonality. And then the ACF and PACF is more concerned with the analysis part. I'm not going to go too much into it because I did cover it in the last series, but recall that the PACF kind of, it's different from the ACF because it kind of removes the previous errors of the lag values. So it's not, it tries to remove the bias from the previous lag values. And so I don't know if I want to say it's more accurate, but generally it will be more useful because ACF, it will be very highly correlated a lot of the times. And so basically we have this data or this equation where the k represents the order, b is the coefficient of the correlation. So generally the higher the b, the higher the absolute value of the b or beta, the higher the autocorrelation will be. And obviously we have statistical tests, tests for everything. We can use these Box-Pearson, Leung, I think is how you pronounce it, Leung-Box Q statistic test to see if there is autocorrelation within the time series data. Alright, that's going to be it for the first video. Again, this is kind of a general viewpoint, mostly, again, first order properties, and as I move along the series, I will go more specifically and use these second order properties to analyze the time series plots and how I could predict use these models to forecast in the future.